undergraduate from the University of Michigan. As you can see, I've been brought here today to talk about my summer undergraduate research in engineering project, which is of great interest to my interviewer. So this summer, I've been working on developing a novel sensor for soft actuators. But first, let me explain a little bit about soft actuators. Well, a soft actuator is exactly what it sounds like. They are soft, flexible, and compliant actuators. The one that I've been working so far throughout the summer, they are called McKibben artificial muscles, just like muscles. Well, it's a pneumatic actuator that works by having air pumped into a tube. So when the air fills up the chamber of the tube, with the ends sealed, it expands laterally and it contracts longitudinally, just like how biological muscles work. When you flex your arm, it expands sideways while contracting. Well, you see, nowadays we have fairly advanced rigid metallic robots in the industry, and they are very precise, efficient, and effective in manufacturing plants. But if you take them out of the controlled environment and put them in a more unpredictable or harsh environments, they will struggle. And this is why soft robotics is gaining such attention right now, due to inherent properties that the soft materials provide, like being compliant, being soft and flexible. They are ideal to be used in situations like this to interact with more natural or harsh environments, and especially when you need them to interact with living beings like humans. As for me, my PhD mentor has actually come up with an innovative way to sense the movement of these actuators. It's called the smart braid. So the braid functions by using a fundamental electrical property, which is inductance. The smart braid is a braid which is made out of conductive wires, and it wraps around this McKibben artificial muscle. And this conductive wires, they form one whole circuit. So when the muscle contracts, the braid follows its shape and contracts with it. This causes the braid fibers to align when it contracts, and then it causes the inductance to increase. So by measuring the increase in inductance or decrease when you deflate it, we can actually track the contraction of the muscle itself, which gives the muscle, this actuator, its self-sensing capabilities. So mainly I ran experiments and processed the data to compare the performance of our novel sensor against a proven one, like the potentiometer. Now that is a great question. Like I've explained before, soft actuators have a lot of advantages. They are light, they are flexible, compliant, and fairly inexpensive. But there is one major hurdle in using these soft actuators, which is feedback control. Feedback control is difficult to be implemented because the sensing capabilities of the actuators themselves are quite limited. Take the encoder for example. The encoder is a very conventional sensor. It's used commonly in robots nowadays to do feedback control. But the thing is, encoders are quite expensive and they are actually very fragile as well. So it's quite unsuitable to be used in harsh environments or unpredictable situations that the soft robotics are all about. Plus, you require rigid joints and precise locations to attach these sensors to. So in general, traditional sensors, they don't work very well with soft robotic elements, and that is why the smart braid is a good alternative to provide position control, because it senses the length of the muscle that it wraps, and using this you can do feedback control